my dear students, and I want to welcome you to this semester's first video help session. I quickly want to talk to you about what's expected in 2.1. In general, I'm going to post video help sessions a few days after I post assignments, hopefully before they're due, unlike this one. But I want you to see how to work things and how I work them. But I have to warn you, depending on what college I'm talking to, I'm wearing a PCCUA tie, I'm doing and have up PCCUA kit, if you will. But what I also have is a laboratory I'm coming to you from at CR College, and as an adjunct with an online video course, I teach at several other places as well. So, your mileage may vary. In addition, depending on which school, which semester, even which person you are, depending on the school and the LMS, Learning Management System, Blackboard, Canvas, the old Blackboard, WebCT, etc., you may have questions that scramble the answers or even change the values, and I'm always changing the values. So read the question, don't copy. It won't do you good. When you open up your course, you will see when you sign into your school's whatever you call it, dashboard. It may be the Microsoft version, most of them are, or others. Your course LMS, Learning Management System, may be Canvas or Blackboard, but variably, when you open up Canvas or your LMS, you'll see your courses there. Your mileage, again, may vary because I've got an instructor view, but you'll see your selection of courses there. And when you go to your course, you go to your course content, whether it's called course content or course assignments or course modules. And I have modules up here that you can't see. But on this first exercise, exercise 2.1, when you go to it, download it, you see something that looks like this, okay? And so, there's several questions here. Which of the following elements exist as diatomic molecules? And I give you a list of elements. And there are a number of them. I was taught if it ends in gen or ene, it's diatomic. Hydrogen, oxygen, nitrogen, fluorine, chlorine, bromine, iodine, hydrogen. Those are all diatomic elements. Sulfur can exist as a diatomic element, but it is not one of the choices. You'll see it on the test. So, I'm not going to answer this because depending on what version you have, there will be different answer choices. So, you can just Google each individual element or look it up in your online textbook in Chem Libre. For example, these questions came directly from Chem Libre. You know, there's only so many ways to test to see if somebody understands this concept. And, you know, this is one way. This one has a basic concept check where we have we have a chemical reaction going where we burn methane, which by the way is CH4, and also known as swamp gas, or it's a form of, I guess, natural gas, methane or ethane. It's burned, you have 32 grams, and you burn it in oxygen, and you combine it with 128 grams of oxygen, and you get 88 grams of carbon dioxide and water produced. And you produce carbon dioxide and water. And if you look at the numbers, no matter what your numbers are, because the numbers vary from semester to semester, I had 32 grams of methane and 128 grams of oxygen. If you add those up, that adds up to 160 grams. And I produced 72 grams of water and 88 grams of carbon dioxide. And again, we end up with 160 grams because the masses of the reactants equals the masses of the products, okay? Matter is neither created nor destroyed, and this is called the law of conservation of mass. In this particular example in C, yours may be different. But now, it asks, you have a sample of methane, contains only carbon and hydrogen, and 3 grams of hydrogen for every 1 gram of oxygen. Where does that come from? Well, carbon, if you look at it, its molecular mass is 12. I will say it's 12.011. It's close to 12. Atomic mass units, Daltons, I like to just go straight to grams per mole. And I'll explain that in another lecture later. This hydrogen has a mass of 1.00794. Okay? Which for my purposes is 1. But there's 4 of them, so I have, for every molecule of carbon, of methane, I have 1 carbon, 4 hydrogens, and by mass, that is a 12:4 ratio, okay? And this is where most people make a mistake, especially if I give you a multiple choice set of answers. Because if I have a sample of methane that weighs 4 grams, what? 3 of those grams are going to be carbon, and 1 of those grams is going to be hydrogen. Because hydrogen is 1/4 of the total. 4 is 1/4 of 16, and carbon is 3/4 of the total. So, the question asks, if I have a different 75 gram sample, how many grams of hydrogen would be in there? And people go, oh, it's 3 to 1, so 75 divided by 3 is 25. You would be wrong, okay? It's not asking the stoichiometric ratio of carbon to hydrogen, it's asking what's the ratio of hydrogen in methane, in the total. So it's 1/4 of the total mass. Hydrogen occupies or takes up or contributes 1/4 of the total mass of methane. So my answer would be, if I have 75 grams of methane, or methane, if you learned it from the Australian instructor that I learned it from, and we want to get grams of hydrogen. I have 1 gram of hydrogen per what? 4 grams of methane, do you see how my grams of methane cancel? And I'm left with an answer in terms of grams of hydrogen. And it would be 75 divided by 4 grams of hydrogen, which is what we ask. How much hydrogen in grams would be present in that 75 gram sample? And 75 divided by 4 is equal to 18.75 grams of hydrogen. Now, to be a bit more accurate, I have 3 significant figures here, 3 significant figures here. So the best answer would be 18.8 grams of hydrogen. I grew up in Europe, and I write my 7s like this. I write my Zs like this, and I call them a Z, not a Z. And I was taught, I do my division differently too, but I was taught to round to the nearest even number. And that way you round up and down as often as one or the other, and you spread your error out. In America, I know you're taught to always round up. Well, in this case, we arrive at the same conclusion. But if it were 18.85, I would have rounded down to 18.8, not up to 18.9, as you would do. But I will take that into consideration if I need to during our grading. Let's go on to the rest of this assignment and quickly discuss what I want. It asks, what are the 6 postulates of Dalton's atomic theory? And it depends on where you Google and where you look this up. I asked you to consider that you are using your textbook on Chem Libre. And I could show you the link, but you can find it. It's in section 2.1, Atomic Theory of Matter. So depending on who you ask, Google or ChatGPT or your textbook, people say there are various numbers of postulates in Dalton's atomic theory. I've even heard people split some of them apart and get as many as 11. In general, they're between 3 and 6 postulates. Those are, and I'm not going to write them down or give you any time, just listen. He said that all matter consists of individual atoms, indivisible atoms. Atoms of the same element are identical, and there's a corollary to that, and that is if you have different elements, then you must be made up of different kinds of atoms. And he stated it as atoms of different elements are unique. They're different. Compounds are formed by combining atoms. Water is a compound, H2O. I combine 2 hydrogens and 1 oxygen atom. And atoms combine in simple whole number ratios. 2 hydrogens to 1 oxygen. In water, there's a water molecule. A red oxygen and 2 white hydrogens. Methane, which we just talked about. 1 carbon to 4 hydrogen. Now when you get into biochemistry and large compounds like proteins, like hemoglobin in your blood or something, the numbers no longer are simple little ratios. When you talk about the molecular composition of hemoglobin, you'll have hundreds and thousands of atoms. But for most compounds in the chemical storeroom back here, they're simple whole number ratios, and most of the time you don't even have to take your shoes and socks off. 10 or less for many inorganic compounds. And number 6, chemical reactions are rearrangements of atoms. Atoms are retained, but just rearranged, okay? Except in, for example, a nuclear reaction. Which brings up the next question. we know that many of these have been proved wrong. Many of his postulates are not maybe entirely correct. For example, I said all matter consists of indivisible atoms. We know now you can divide up an atom. Now, atom is the smallest quantity of matter that retains the property of that matter, but I can divide it up into protons, electrons, and neutrons, and we can subdivide those up into quarks and antiquarks and muons and gluons and other subatomic, subatomic particles. So, it's not indivisible. And, it can neither be created nor destroyed, and yet you can interconvert matter and energy, and you can convert energy into different forms. So, it says atoms of the same element are identical. We know now about isotopes, for example. For example, my carbon, I have carbon 12, but with every breath I take, the CO2 I'm breathing out, 99% of those are carbon 12 with a mass of 12, 6 protons. It has to have 6 protons or it's not carbon, but also 6 neutrons. We ignore the electrons. Very little mass. It takes almost 2,000 of them to equal 1 proton. And we only go up to 118 in our periodic table anyway. Those, and there are other factors to consider in more advanced courses. But some of that carbon is carbon-13. And there's also a radioactive form, an unstable isotopic form, carbon-14, with 8 neutrons. It starts to get unstable, therefore it's radioactive. So we know that isotopes are different forms of the same atom with the same number of protons but different numbers of neutrons. So not all atoms are identical of a given element. And then we learn that chemical reactions are rearrangements of atoms, and that's true, but there are, for example, nuclear reactions where atoms break down, and there are not chemical reactions, but physical changes that don't require rearrangement, for example. Although there may be some rearrangement of intermolecular forces, and bonds, which we'll talk about another time. So, lots of those postulates are not entirely or 100% accurate or valid, or you have to talk about exceptions. And then finally, the last question asks, what about the radius of an atom? And once again, your mileage may vary depending on what value I get you. But I want to make a point of something. And, that atoms are mostly empty space, and they are very small. So, it says the radius of an atom is approximately 10,000 times larger than the radius of its nucleus. So, if I draw my radius this big, my first electron, let me draw this on the board. If I'm drawing hydrogen, for example, we draw it here. But if my nucleus, my 1 proton in the nucleus of hydrogen, if I had deuterium, it'd be a proton plus a neutron. Let's take a deuterium atom, an isotope of hydrogen. We draw it on the board like this, 1 proton, 1 neutron, 1 electron. But this distance here, compared to this distance here, if I make this distance 1, this distance here is 10 to the 4th times that. In other words, I need 10,000 of those before I get to the first electron. The point of this is just to say that atoms are mostly empty space, okay? And so, I'm putting a break in this because that electron would be 10,000 of these. not quite a meter, but it'd be half a mile in that direction, okay? So, the example I have says, what if the diameter of the nucleus was 2 meters? That's the diameter. So if the diameter is 2 meters, the radius would be equal to, if the diameter is equal to 2, the radius would be equal to half that, right? Because our diameter is all the way across the circle, and our radius is from the center. Okay? So this is a radius, and this whole thing here is a diameter. Anyway, if the radius was a meter, then the electron, or the radius of the whole atom, would be times 10 to the fourth, or 10 to the fourth meters, or 10,000 meters. 1,000 meters is a kilometer, so it would be 10 kilometers. And the next question asks for conversion that I will never ask you. I will never ask you to do metric conversions because we're only going to work in the metric system, but this time I'm asking you to put it in terms of miles. And if I have 10 kilometers, I lived in Europe, so we drove American cars when we lived there, but we had to convert to kilometers because everything was in metric there. And the quick way to do it is you take the miles per hour and multiply by 6. If you're going 60 miles, if you're going 60 kilometers an hour, or the speed limit is 60 kilometers, that would be 36 miles an hour on your speedometer. In other words, our mantra was you multiply by 6 and drop the last digit. You really multiply by 0.6. So if that value was 10 kilometers, it would be 10 times 0.6, or 0.6 times 10, and that would give us miles. And to do your units, if I have 10 kilometers and I have 1 mile per 0.6 kilometers, my kilometers cancel and my answer is miles. 10, not divided by 0.6. What did I do? Sorry. 0.6 miles per 1 kilometer. I got my conversion factor wrong. Then I would have kilometers cancel and 6 miles for my answer. Again, I may have given you a different diameter or radius, but that's how you do the math. You multiply, you divide your diameter by 2 to find your radius, you multiply your radius by 10 to the fourth, and then you convert to miles using the conversion factor I've given you, and that's the answers to your first, or how to answer your first one. I won't give you a video help session for everything, especially if it's looking up chemical names and formulas and the like, but if there's quantitative aspects to it, in general, I will be posting a video help session a few days after it's posted. So go to your assignments, keep up, don't fall behind. Call or text me if you have any problems, 870-377-3499. Call or text anytime, and I'll call or text back when I have the time, but as soon as I can. And until then, stay safe. Goodbye now.